SwayamPrabha. Digital India. Educated India.
In this lecture, we are going to discuss the work energy relation. Now, to understand the work energy relation, we have to look at the Newton's second law of motion. Actually, this work energy relation is an integral of the Newton's second law. Therefore, it will not generate any new information that is not already present in Newton's second law. This relation will finally lead us to the conservation of energy in certain systems. Let us start with the Newton's second law then. As you know, for a particle of fixed mass m, this is what Newton's second law reads: mass times acceleration is equal to the net force acting on the particle. If you take dot product of both sides of this equation with the velocity vector, as you can see, I have taken dot product with r dot, which is the velocity vector on both sides. The left hand side can be written in this form as a total time derivative of half m dr dt dot dr dt, and you can check this. If you take the derivative, it is a derivative of a product, then you will get m r double dot dot r dot. Therefore, you recover back the left hand side which I have written previously, and that must be equal to force dot the velocity vector. Now, you know that this expression half m dr dt dot dr dt is nothing but half m v square, because it is r dot dot r dot is r dot square, basically velocity square. This is velocity square, magnitude square of that vector, which is velocity square, and this is the expression of kinetic energy of the particle. Therefore, the left hand side I can write as d of the kinetic energy, and this dt I take to the other side. Therefore, on the right hand side I have f dot dr dt into dt, and that is nothing but f dot dr vector, and f dot dr vector is nothing but the work done by the force on the particle. If dr is the infinitesimal displacement, then f dot dr is the infinitesimal work done, and if you are moving from this point A to B, I have integrated this whole equation from as the particle moves from this point A to this point B. So, the particle is moving on a certain path under this force from point A to point B in the Cartesian space, let us say. Therefore, I can write this in a condensed form as the kinetic energy of the particle at position B minus kinetic energy of the particle at position A, that is T b minus T a, that is obtained by integrating dt. It is quite straightforward, and that is equal to, this is the work done as the particle moves from A to B. This is the work done by the applied force, the net force that is acting on the particle. This is the work done by that net force as the particle moves from position A to position B. This is known as the work energy form of the Newton's second law. This is an integral of the Newton's second law. Why do we call it an integral of Newton's second law? Because it involves one derivative less than Newton's second law. Newton's second law involves acceleration, which is the double derivative of the position vector, whereas here, because it is kinetic energy, it involves only velocities. This gives us a scalar relation. This is the second important thing to notice. The work energy form gives us a scalar relationship. Therefore, it is an integral of Newton's second law and a scalar relationship. Now, this, because it is an integral of Newton's second law, it will not generate new information, right. It already has all that information that is there in the second law. It is presenting in a different form. This is the statement of the work energy relation, which says that the change of kinetic energy is equal to the work done by all the external forces as the particle moves from a certain position to another position. Now, I have written out the explicit expressions of, suppose there is a particle and its velocity at position B is V B and its velocity at position A is V A. In that case, I can write kinetic energy at these two positions half m V B square minus half m V A square, and that must be equal to work done over this path as it moves from A to B. Now, the work done, as we have just now discussed, is F dot dr. Here what I have done is I have decomposed this force vector in two components. One is tangential to the path, which is indicated by Ft, and the other is normal to the path. This is a decomposition of the vector F. So, these are not additional vectors, these are the components of vector F decomposed along these two orthogonal directions. One is tangent to the path, the other is normal to the path. How do you find these things? How do you find these components? The tangential component is very easy to find. It is F, the force vector, dot E t cap, which is the unit vector along the tangent, times E t. Now, F dot E t cap gives you the magnitude F t, and E t cap is the direction of the tangential force. Now, how do you find out E t cap? E t cap is along the velocity, this we have discussed previously. Therefore, it is a unit vector, it is a unit vector along the velocity vector direction. Therefore, it is velocity vector divided by its magnitude. Thus, this is nothing but the unit velocity vector, that is E t, the tangential vector, and you can find out the normal component just by subtracting out from this force. If you want to find out normal vector, the normal vector is nothing but F vector minus F t, and F t is already known. If you just put that expression of F t there, you will get the normal vector, the normal force vector, which is normal to the path. Okay. Therefore, now F dot dr therefore should be only F t dot dr. Why? Because F n is perpendicular to the path, it is perpendicular to dr, F n is perpendicular to dr. Therefore, the dot product is 0. What survives therefore is F t dot dr. You can just substitute this expression here and check. Now, this dr can be written as, this dr vector can be written as the magnitude of shift times Et vector, because dr is tangent to the path. Therefore, it must be proportional to Et cap vector and the length of path is ds. Therefore, dr is ds times Et cap, and when you take dot product of f and dr, remember ft is this, it is already with Et cap, and ds you will get this, where ds is the magnitude of the dr vector. Therefore, finally, what I have is the work done over the path is only produced by the tangent vector, the tangent force, the tangential force tangential to the path. The normal component of the force will not do any work. We can also look at the derivative form of the work energy relation. This we have derived a moment ago. d dt of the kinetic energy is f dot r dot velocity, f dot velocity. Now, f dot velocity is nothing but power. Therefore, I can write this left hand side as d kinetic energy dt is equal to the power. This is the differential form of the work energy relation, which you can put again in the integral form in terms of power. Therefore, kinetic energy at position B minus kinetic energy at position A is equal to the integral of the power over time, as time moves from T A to T B. So, is the time integral of power is the work which is equal to the change in kinetic energy. Let us look at some special cases of the work energy relation. The first special case is when force equal to 0. Simplest case, kinetic energy will not change, of course, because right hand side is 0. Therefore, kinetic energy at position B must be equal to kinetic energy at position A. Therefore, there is no change in kinetic energy as the particle moves under 0 force or force is balanced. If f dot v is 0, f dot v is nothing but power. Therefore, if power input is 0, then again kinetic energy will not change. Now, think about certain situations where f dot v is 0. One of the situations that will immediately come to your mind is a stone. If you tie a stone at the end of a thread and you set it into rotation, then forget about the effect of gravity. The tension in the string is always perpendicular to the motion of the stone. Suppose this is the stone, then the force on the stone is the tension, and the velocity therefore, this tension will not do any work on the stone. Therefore, if the stone changes its motion, then it is not because of tension at least. If you neglect air, drag, etc., then this stone is going to keep moving. Another interesting situation occurs where f dot v is 0 is of a charged particle in a magnetic field. As you know, if you have a charge, let us call it q, and there is a magnetic field, let us say coming out of the plane of the paper. So, this is our positive charge and there is a magnetic field which is coming out of the plane of the screen, and this charge is given a velocity. How does the charge move? What is the force on the charge in a magnetic field? It is given by the Lorentz force only for the magnetic term. Q times V cross B. Q is a scalar, V cross B. Therefore, force is V cross B is proportional to V cross B is equal to Q times V cross B. Now, V cross B is a vector which is perpendicular to both B and V. What is important here is that it is perpendicular to V. Force is perpendicular to V, therefore, F dot V must be 0. Therefore, this is another case where F dot V is 0. So, this is their example. F dot V is 0 in a magnetic field for a charged particle. The third special case of the work energy relation is when F is negative gradient of a potential, a scalar potential. V is a scalar potential field, that means potential field means at every point in the space, there is a value of this potential. This is also called potential energy function. Gradient of the potential energy function is defined like this, as I have shown here. Gradient is del V del R1, del V del R2 like this, del V del Rn if there are n coordinates. It is also written as del V del R. If the force is negative gradient of a scalar potential field, then let us see what happens. F dot dr, this is the work done, is minus del V del R dot dr, and that must be equal to minus dV. Remember what is, suppose V is this function, V is V of x, y, let us say 2 variables, then what is dV? It is del V del x dx plus del V del y dy, and this is the form we have, because I can write this as del V del x del V del y, this is our gradient of V dot dx dy, and this is this expression, therefore, it must be dV. Therefore, dt integral, that change of kinetic energy, infinitesimal change of kinetic energy integrated from A to B, it must be equal to minus integral of dV. Now, I can bring this integral on the right hand side to the left hand side and write the combined integral as d of t plus v, and this t plus v, kinetic energy plus potential energy, is known as the total mechanical energy of the system. And in this case, in the special case that we are considering, this is the special case we are considering, d of t plus v is 0 integrated from A to B. In other words, the total mechanical energy is conserved. I am writing this t plus v as E, which is the total mechanical energy, and if I do this integral, it is E B, E at the total mechanical energy at location B minus total mechanical energy at location A, that is equal to 0, which means that the total energy at B must be equal to total mechanical energy at A. So, energy is conserved if the force is a negative gradient of a potential function. Now, the question arises when this will happen, when can you say, suppose you are given a force field, force vector, at every location you have a force vector, then it is called a force field. When can a force field be represented like a negative gradient of a potential? This is a question, this is a valid question. If you take curl of both sides of this expression f is equal to negative gradient of v, if you take curl of both sides, then you can see the curl of gradient of a scalar, curl of gradient is always 0. This is a theorem from differential calculus. Therefore, if the curl of the vector field is 0, then it can be represented as minus of gradient of a scalar field. Therefore, if you are given a vector field, for example, I will show you. Therefore, curl of the force field equal to 0 implies both ways, that the force can be represented like a negative gradient of that of a scalar potential. If you take an example like this, f is x I cap plus y j cap plus z k cap, let us say Newton, and x is a position, x y z are position of the particle, then you can check that the curl of this vector is 0, and then you can try to determine what is the potential whose negative gradient is this force field. So, I leave that to you. Okay. So, once again the work energy, the right hand side of the work energy relation, which is the work done as the particle moves from A to B, which is nothing but f dot dr integrated from A to B, and this we had written as del v del r dot dr vector is equals to dv integral. Therefore, this work done is nothing but the change in the value of the potential function. This tells us that the work done when the particle moves from A to B is nothing but the difference in the values of the potential calculated at R B and calculated at R A. It is V R B minus V R A. This does not bring in the path, as you can see. So, it is independent of the path you take. If it is independent of the path, then I have drawn in this figure on the right two paths from A to B. As you can see, two paths from A to B, one goes from A to B, the other goes from B to A. Suppose I calculate the work done so this particle is moving from A to B and then B to A, let us say, and this is in a force field. Let us try to calculate the work done by this force field. So, under the action of this force, these are the two paths. Now, suppose this is, let us say, the upper path. So, this path, then from as the particle moves from A to B, then it is f at all these points dot dr on this path as it moves from A to B. On the other part, the return path, it is this integral, again force on this path dot dr on this path integrated from B to A. And this must be equal to, the first integral must be equal to the potential value at R B minus the potential value of R A, which we have just now seen here. Right. So, it is the difference in the potential value of the potential function at R B and R A and the second integral must be the difference in the potentials at R A and R B, V R A minus V R B. Therefore, now I have traversed a complete path. This integral indicates that it is the closed path. So, integral over a closed path of f dot dr then must be 0, because this right hand side turns out to be 0. Therefore, over a closed path f dot dr must be 0. Now, from Stokes' theorem, this implies that over any area, any curved area which has these paths as its boundary, which is marked in red. Red is the boundary, it is like a pouch. You can think of this green part as a pouch whose boundary is formed by this path. Then from Stokes' theorem, I get this circular integral as curl of f dot n cap. N cap is any normal on this pouch, normal vector on this pouch, times dA, a small infinitesimal area on the pouch, and integrated over this area. This is Stokes' theorem, that must be 0. If that is to be 0 for an arbitrary chosen sets of paths or arbitrary chosen pouch, this area, then it must be true that curl of f must vanish. Therefore, if the work done by a force over a closed path, right, if the work done by a force over a closed path in a force field is 0, then the curl of that force field must vanish. So, net work done on a closed path must be 0. Therefore, if a force is representable as negative gradient of a potential, then its curl, the curl of the force vector must be 0. Now, let us look at what are known as conservative theorems. There is the work energy relation. If f is 0, then we have just now seen that kinetic energy does not change. If f dot v is equal to 0, then also kinetic energy does not change. Similarly, if f is negative gradient of a potential function, then the total mechanical energy, as I have shown here, the total mechanical energy is conserved. Such systems are called conservative systems. They conserve energy, mechanical energy or kinetic energy, and in such systems, if there is a force field, then it must be a conservative force field. If it is a conservative force field, then such systems are called conservative systems, because it conserves energy. Then the question arises, what are non-conservative force fields or non-conservative systems? Wherever the force is a function of time or velocity, force is a function of velocity is you may know, it is very common, damping, viscous damping has a force which is dependent on velocity. Such systems are non-conservative, excluding of course this case where f dot v is 0, like a particle in a magnetic field, a charged particle in a magnetic field, where f dot v is 0 and then it becomes conservative. So, the force is velocity dependent, but it is still conservative. Then friction, dry friction, let us say, there also it becomes non-conservative. So, these are non-conservative force fields. In general, therefore, we can have the change in kinetic energy is integral of the conservative and the non-conservative force fields, sum of them, because the total force field must be can be divided into two parts. One is the conservative force fields and the non-conservative force fields, and the total force field is the sum of these two, vector sum. Now, the conservative part can be written, conservative force can be written as negative gradient of some potential, and we have discussed this, that negative gradient of v dot dr is dv. That I can bring on the left hand side and combine it with the kinetic energy to form the total mechanical energy. Therefore, in general, this is the most general form of work energy relation, which says that the change in mechanical energy is equal to the work done by all non-conservative forces over the path, where E, the total mechanical energy, is kinetic energy plus potential energy. Let us look at some examples of potential force fields. Spring force, F is equal to minus kx is on the mass. This force acts on the mass. I have shown the free body diagram, and you can check that if the spring is stretched by a distance x, then the force on the mass is minus of kx. Therefore, minus of dv dx, which is the force, is minus kx. Therefore, V must be half kx square. Uniform gravitational field, force is minus mg j cap. I have shown a diagram which shows the free body diagram of the mass, and I have chosen the datum as the ground from where y is being measured. Now, the negative gradient of the potential, so I want to find out the potential. The negative gradient of the potential, which is equal to the force, is minus mg j cap. Now, I look at the components. Del v del x is 0, that means the potential is only a function of y, and del v del y is mg, which is the force due to gravitation, uniform gravitational field. Therefore, V must be a function of only y, and by integrating I get V must be equal to mg y. Let us look at the gravitational field of a point mass. This is the negative gradient of the potential in polar coordinates. This you can check. Negative gradient of a scalar potential in polar coordinate. This is the operator. Del del r E r cap plus 1 by r del del theta E theta cap. And if when this acts on the potential V, I have this. So, negative gradient of the potential, that must be equal to F, and you know that from Newton's law of gravitation it must be minus g m m by r square, and in the E r cap direction. That negative comes because it is in the E r cap, negative of the E r cap direction. From here, by comparing the two sides, del v del r is g m m by r square and del v del theta equal to 0. Therefore, V must be a function of only r. And if you integrate, V turns out to be minus capital G capital M m by r. To summarize, we have looked at the work energy form of Newton's second law. As I have mentioned, this is an integral of the Newton's second law and does not generate any new information which is not already present in Newton's second law, and this leads us to the conservation of energy. We have looked at conservation of conservative systems, conservative force fields, and also non-conservative force fields where energy is not conserved. So, with that I will close this lecture.